All right, let's walk through this projectile motion example slowly, even if we've gone over portions of it in class. So the problem at hand is that we're going to fire a cannonball from a cannon that's angled 30 degrees above the horizontal, so this angle right here, and it's going to fire out of this cannon with a velocity of 20 meters per second, obviously pointed at the 30 degrees of the cannon. So if we neglect friction and air resistance and all sorts of frictional effects, how far from the cannon does the cannonball actually land? Right, so we're asking to find this delta x distance. Right, so the strategy is that we are going to use the concept of orthogonality so that we can treat this curved path trajectory as a set of two 1D problems instead of a full 2D problem. The idea is to take the initial velocity which we're given and break it into an x component and a y component. So then we know that because they're independent, we have a problem where it starts off with a certain x velocity and it travels a certain distance in x, and there is no acceleration in that direction. Once this thing has been launched by the explosion, the gunpowder or whatever else, it is just going to be coasting along here in the x direction with no additional forces. Gravity, of course, is acting on it, but gravity points completely in the vertical direction, and the orthogonality principle tells us that the gravity acting in the vertical direction does not affect the horizontal direction at all. So that means that we can solve the vertical freefall problem for duration. We've already done that, right? If we have a problem that says I have a y component to my velocity, which I can calculate because I know the angle and I know the total velocity. So I have a y component to my velocity. It gets launched up with that velocity. It gets slowed down by gravity pulling downwards, an acceleration due to gravity pointing downwards, until it eventually comes to a stop. This is like our basketball reaching the shelf problem that we did last lecture. So then it comes to a stop, and then gravity will pull it down and start accelerating it downward until it hits the ground again. So we have enough information to solve that problem entirely, right? Which means that we can get the duration for how long between when I launch it up and it comes all the way back down and hits the ground. Once I know how long the ball is in the air, we can calculate, since the ball is not actually just moving straight up and down, at the same time it's moving in the vertical direction, it's also moving in the horizontal direction. But of course, by the time it has vertically hit the ground again, it will hit the ground over here. And that's what we're asking for. We want to know where it is by the time it touches the ground again. So if we know the duration of the motion this way, we also know the duration of the motion this way. And if we have the duration and we know its initial velocity in the x direction, then we can easily figure out the displacement from delta x equals v delta t, because there's no acceleration in the x direction. So let's go about doing that. Again, we start off by asking always, what is our goal? Our goal is to calculate how far from the cannon does the cannonball land, and that implies how far is it landing in the horizontal direction, right? So we want to calculate a horizontal displacement, delta x, of the cannonball when it hits the ground again. So we first start, as always, by drawing a sketch of our problem. That always helps. Picture is worth 1,000 words. So we have some initial velocity, which we can break into a y component and x component. We have gravity pointing downward, and we know the angle of that velocity vector, 30 degrees above the horizontal. Okay, we'll choose our origin to be at the point where the cannonball is launched. So this point here is x equals 0 and y equals 0. So as we said, we're going to break this problem into two individual one-dimensional problems that are linked by time. So first, we need to get the x and y components of the initial velocity. The x component is just magnitude of v cosine theta, which plugging in numbers gives us 20 meters per second for the magnitude of velocity times cosine of 30 degrees, gives me 17.32 meters per second. So we'll hold on to that number. In the y direction, the y component of the initial velocity is going to be initial velocity times sine of theta, and that gives me 10 meters per second after we plug into the calculator. So what we're going to do now is we're going to start by focusing on the vertical aspect of the problem. Right? And this is just stated, usually, but you're probably asking, wait, what? How do we know to focus on the vertical problem rather than the horizontal problem? Right? Where did that come from? It comes from experience to some degree that we know to do this, but for those of you who lack the experience, which is why you're students, let's see if we can break this down into some sort of logical process for figuring out how to tackle this problem. So how the heck do we know to focus on the vertical first? Well, let's, as always, go back to asking what our ultimate goal is. Right? We want to have this goal-oriented problem-solving mentality. So our goal was to find horizontal displacement. Right? If our goal is to find horizontal displacement, then how did we know to go vertical first? Well, let's look at this. If we're trying to solve for horizontal displacement, we need to ask what tools do we have, what equations do we have that will help us solve for this horizontal displacement. Right? One easy and obvious answer is that if I know the velocity, right, then, and I know the time, I can calculate displacement just by the definition of velocity. Right? V is equal to delta x delta t, which means delta x is equal to v times delta t. So can we use this tool? Right? What information do we have? Oh, and the reason we can use this equation, this simple equation, is because there is no acceleration in the horizontal direction. Remember, the only acceleration, the only forces acting are, I shouldn't say force because we haven't talked about force, but there's no acceleration in the horizontal direction. Only gravity is acting on the ball, on the cannonball, and it's acting in the vertical direction. And we know those two directions are independent. So x is very simple. It has velocity. It travels for a certain amount of time, but there's no horizontal acceleration acting on the cannonball. What information do we have? Right, so the initial velocity is given and the initial angle. But I'm still missing both vxi, which is the initial velocity component in the x direction. That wasn't just given. They didn't say it has an x component of this much. They just tell me what the total velocity is. And I'm also missing delta t. They don't tell me how long the cannonball's in the air, right? So I'm missing two pieces of information. So now I got to figure out if I can get those two pieces of information. If not, then this is not the right tool to use. But let's not give up quite so easily. Well, we already stated that we can figure out very easily from geometry, trigonometry, that Vx is just magnitude of v times cosine theta, and Vy is magnitude of v sine of theta, and both of those pieces of information are given to us. The magnitude of v was, I believe, 20 meters per second. Yes, 20 meters per second, and the angle is 30 degrees. So we now have Vx and we now have Vy, something that we can easily solve for. So looking at this equation, if I have Vx and my ultimate goal is to get delta x, then all I need is the duration, delta t. We just need to find delta t and we are golden. We can figure out delta x and we're done. Problem is that we can't do this with the horizontal equation. Because you see with this equation, we're trying to figure out delta x. We need to know delta t, so that's two unknowns for one equation, and that's not a solvable problem. So that means we have a secondary goal. In order to get delta x using this equation, I first have to find delta t. So what other equations, what other tools do I have that make use of delta t so that I can maybe rearrange it to solve for delta t? Well, we could use one of the vertical kinematic equations, right? The reason we have any hope that we can make better progress with the vertical equations when we couldn't get there with the horizontal equations is that we have one extra piece of information in the vertical direction, and that is we know the total displacement, right? In x, we don't know the time and we don't know the total displacement. That's one of the things we're trying to figure out. But in y, the total displacement is known because we're asking for how long and how far it is gone before it hits the ground again. But by definition, if it was shot off from the ground and it ends up at the ground again, then in the y direction, its displacement is 0. It ended at the same height that it started with, from 0 to some height, but back down to 0. So by the time the cannonball lands, it is returned to its starting height. And so we have this extra piece of information that might help us make progress. So for the vertical problem, we want to know the time that the ball goes up, turns around, and makes it back down to the ground. So that is to say we're interested in a final condition where final position for y is 0. That means we now know the initial and final positions of y. We know the acceleration, that's just the Earth's gravity, and we want to solve for time. So it looks like the appropriate equation that we're going to want to use, the kinematic equation, is the one that's missing information on velocity. Because you see we have initial and final y position. We have initial and final acceleration because the acceleration never changes. And we're trying to solve for time. The one thing that's not mentioned is velocity. Right? We don't have the final velocity. It's not given to us. So amongst these equations, we can look and say, well, the one missing velocity is this guy. Right? And I can solve, this one allows me to solve for the displacement in terms of the time and the acceleration, if I know the initial velocity, and I do. So we're going to use this equation. We're going to use the y version instead of the x version. Displacement is equal to the velocity times time plus 1/2 times the acceleration times time squared. So we rearrange this because we want to actually solve for duration, right? We got to remember what our goal is. Our secondary goal is to solve for duration, time, so that we can go back and solve for our primary goal, which was displacement in x. We rearrange this equation so that we have delta t on this side. And this actually, if you look at it, has the form of what's called a quadratic equation. If you remember from algebra, this looks like your equation, which is normally written as ax squared plus bx plus c is equal to 0. And that equation, this quadratic equation, has this known solution. We won't derive it, of x is equal to minus b plus or minus the square root of b squared minus 4ac over 2a. You can look that up in your math textbook. So in this case, delta x, or x, is actually delta t. That's the thing that's squared. Right? So there's an x term here. There's delta t term squared. There's a single delta t here that corresponds to this x. There's a term that doesn't have the delta t or the x, and that's all equal to 0. Right? So if you compare these two equations, you can see that blue a, which is the standard form of the quadratic equation, is actually 1/2 ay. That's the prefactor in front of the x squared or delta t squared. B, which is the prefactor in front of the x, which would be the delta t, is just byi, the initial y velocity. And then c is just minus delta y. Right? That's corresponding to this term. And of course, as I said, x is delta t. So then we can just plug these things into the known solution for the quadratic equation and solve for x, or in this case, delta t. So we plug in b plus or minus b squared minus 4ac over 2a. Okay, and we can do this, and this does work. And there are times when you will have to solve the equation using this. But in this particular case, there is an easier way. Because delta y is equal to 0, right, then yi is equal to y final is equal to 0. Initial and final positions are the same. This wouldn't work if we shot from the top of a hill onto a plane, or if we were asking about the position of the ball or the time of flight when it clears a fence, so that its height is not the starting height. But in this case, because delta y between the final and initial conditions is 0, they're all the same. And because delta y is 0, this simplifies to this equation, right? And now what we can do is we can factor out a delta t. So pull a delta t out front, and this just becomes this term plus 1/2 ay, and now it's a single delta t here. But I can just get rid of this delta t, right? I can divide both sides by delta t. 0 over any number is still 0. And so I'm left with 0 is equal to vyi plus 1/2 a delta t. So now I can solve for t by bringing the initial velocity over to this side, taking this prefactor of ay over 2 and dividing it on both sides, and I'm left with delta t is equal to 2 vy over a with a minus sign. So now we can plug in numbers. Plug in the numbers, and we get the delta t. Right, so here's our equation that we just derived. Delta t is equal to 2 times 10 meters per second, because that was the initial y velocity, right? Total was 20, but we worked out early on that the y component of the initial velocity was 10 meters per second. And then we divide that by the pull of gravity, 9.8 meters per second squared. Plugging it all in, we get 2.04 seconds. So that's how long the ball is in the air when we analyze the vertical direction. But because time is time, that's how long it's in the air when we analyze the vertical direction. That's also how long it's in the air when we analyze the horizontal direction. So now we know how long the cannonball is in the air, and we can calculate the horizontal distance that it travels in that time. And because the only acceleration is in the vertical direction, the horizontally the ball is only moving with a constant velocity. And so it's a very simple problem from here on in. For constant velocity motion, we just use kinematic equation number 3 and simplify it to delta x is equal to v delta t. Right? This is really just a definition of velocity, which gives us 17.32, because we worked out at the very first step the x component of that initial velocity. And we now know the time, and that gives us a final answer of 35.3 meters of horizontal travel before it hits the ground.